This is the recap for Lecture 10 of Formal Methods. So the next group of theorems and axioms that we have are about disjunction. We have, looks like 5 axioms here. 3.24 is symmetry of or. P or Q equals Q or P. The second one is 3.25, associativity of or. P or Q parentheses or R is the same as P or parentheses Q or R. So that's the associativity. And then 3.26 is idempotency. P or P equals P. 3.27 is distributivity of or over equivals. P or parentheses Q equals R close parentheses is equivals. P or Q equals P or R. And finally, the last axiom is 3.28, excluded middle. P or not P. Okay, so those are the axioms, and of course we will not prove any of these. These are all assumed. These define the properties of disjunction, the or operation. And so we have 4 theorems at the bottom of the slide here. The zero of or, 3.29, is P or true equals true. 3.30, the identity of or is P or false equals P. 3.31 is distributivity of or over or. So or distributes over itself. We have P or parentheses Q or R equals parentheses P or Q close paren or open paren P or R close paren. And finally, this very interesting theorem, 3.32, that's that we're going to use in several of our proofs later on. Okay. We're going to start now with a heuristic, paragraph 3.33 in our textbook. And this heuristic, do you remember what a heuristic is? It is a rule of thumb or a guideline. And this heuristic says, to prove P equals Q, transform the expression with the most structure, either P or Q, into the other. So let's do an example. We are going to prove 3.29, P or true equals true. Now, do you remember that one way to prove this is to start with the whole thing and get it to a previously proved theorem? But we learned this proof technique meta-theorem that another way to prove it is to start with one side and get it to the other side of the equivalence. Start with one side of the equivalence and get it to the other side of the equivalence. So our question is, which side do you start with? In other words, do you start with P or true and try to get that to true? Or do you start with true and try to get that to P or true? Do you see? You can either start with the left-hand side or the right-hand side. And this heuristic says that you start with the side that has the most structure. So think about it. On the left-hand side of the equivalence, we have P or true. On the right-hand side, we just have true. Which one has more structure? Well, obviously, the one on the left-hand side, P or true. That is the side with the most structure. Therefore, that's the side that we start with, and we get that to be true. To the right-hand side, we get that to be true, which is on the right-hand side of the equivalence. So here's our proof. We write down the word proof, and if you're doing this on paper, by hand, you underline that word proof. Okay. And we start with the left-hand side. So we start with P or true. Now, the first step in this proof is to use 3.3 with Q replaced by P. Maybe we should take a minute and go back and see what 3.3 is with Q replaced by P. I didn't put it in the hint here, but let's go check that for a minute. Okay, so here is 3.3 axiom identity of equivalence, and it's true equals Q equals Q. So with Q replaced by P, that would be true equals P equals P. Now let's go back. So here we are, and so what we're going to do is we are going to replace that true with P equals P. So we bring down the P or, and then in place of the true, we have P equals P, because 3.3 says that true equals P equals P. So we're substitute equals for equals with Leibniz, and we have P or P equals P. Now, the next step, we're going to use one of these theorems we just looked at, 3.27, with QR replaced by PP. Now let's see what that is. 3.27 with QR replaced by PP. So here is 3.27, axiom distributivity of OR over equivals. And you see it's P or open paren Q equivals R equivals P or Q equivals P or R. And if everywhere there's a Q, you replace it with P, and everywhere there is an R, you also replace that with P. What do we have? We have P or open paren P equivals P, close paren equivals P or P equivals P or P. So let's go back. So in place of P or P equals P, what do we have? P or P equals P or P. All right. And so now the next step is 3.3 with Q replaced by P or P. Now do you remember what 3.3 was? It was true equivals Q equivals Q. So if we replace Q with P or P, we have true equivals P or P equivals P or P. So by Leibniz then, that equals true. And we have gotten the left-hand side to the right-hand side. Now, to show you how difficult it would be if we started with the right-hand side, what would that proof look like? It is more difficult to start with the right-hand side, so let's do it and see what, even the very first step would be kind of obtuse. So here's our proof starting with the right-hand side. So now we're going to start with true. So now here we have true, right? So what's the next step? Well, it's not obvious, but here's the way you would do it. We would use 3.3 with Q replaced by P or P. And then what would that make it? That would make it P or P equals P or P. But then you would think, but that's not obvious. That's like, where did that come from? Why are we doing what? We're starting with something simple and we're making it more complicated. That's like pulling a rabbit out of a hat. The next step would be 3.27 with QR replaced by PP, which would be P or P equals P. And then we would use 3.3 with Q replaced by P, and we would get P or true. And that is a valid proof, but that would be very difficult to... You see, it's easier to start with something more complicated and simplify it than it is to start with something simple and complicate it, because you have to complicate it in the direction of the more complicated side. So the bottom line is this principle. Structure proves to minimize the number of rabbits pulled out of a hat. You know, when you see a magician's show and the magician has a top hat, a big black top hat, and he reaches into that hat and he pulls a rabbit out of the hat, and everybody in the audience says, "Oh, where did that rabbit come from?" So in the first step of this proof, which is here, we could say the same thing. Where did that P or P equals P or P come from? Why are we doing that? You see, that's pulling a rabbit out of a hat. So the principle is to make each step seem obvious based on the structure of the expression and the goal of the manipulation. And the best way to do this is to start with the more complicated side and get it to the simpler side. It's easier to simplify than it is to complicate. So that is the principle of starting with the side that has the more structure. Okay, the next group of theorems are concerning conjunction, and the primary axiom that defines conjunction is called the golden rule. The golden rule is 3.35, and again we will not prove it because it's an axiom. And it's P and Q equals P equals Q equals P or Q. And from this one axiom, all the rest of these theorems follow. Symmetry of and, associativity of and, idempotency of and, identity of and. Notice that these are all now theorems. They're not axioms. Zero of and, distributivity of and over and, contradiction, and then we have this group of 4 absorption theorems, 3.43 and 3.44. All right, so let's see how these work. Oh, here's some more. There's some distributivity. Or distributes over and distributes over or. There's this consensus theorem. And then these De Morgan laws are one of the most important laws in computing. These crop up all the time in programming and in hardware, the De Morgan laws. Let's just look at them for a minute. De Morgan A says not parentheses P and Q, close parentheses, equivals not P or not Q. And De Morgan B is not parentheses P or Q, close parentheses, equivals not P and not Q. So you see what happens is when you have a not outside of a parentheses with a conjunction or a disjunction, what it does is the not goes in front of each of the operands, the P and the Q, and the and changes to an or, and the or in part A, and the or changes into an and in part B. Okay, so let's see how the golden rule works to prove some theorems. Like we mentioned before, the golden rule defines conjunction in terms of disjunction. And the first proof that we're going to do is 3.39, identity of conjunction. P and true equivals P. Okay, so here we go. Here's the proof. We're going to start with the whole thing on this time. Now, do you see P and true equivals P? Do you see that looks like part of the axiom golden rule? In fact, if you look at the golden rule, 3.35, and everywhere there's a Q, you replace it with true, what do you have? Can you visualize what's going to be in the rest of the hint as we write, when we write it out? It's going to be, well, everywhere there's a Q, replace it with true. So it's going to be what? P and true equivals P equivals true equivals P or true. Like this. Okay. And now what do we have? We have P and true equivals P. Well, by 3.35 with Q replaced by true, that's the same thing as true equivals P or true. Right? So we wind up with, on the next step, true equivals P or true. Now we are going to use symmetry of equivals. Symmetry of equivals says P equivals Q equivals P. And what it says is that we can switch around. When you have an equivals, you can switch the left-hand side and the right-hand side. So by 3.2, we will flip them around so that we have P or true equivals true. But P or true equivals true by 3.29 is the zero of or. Let's check that. Sure enough, 3.29 is a zero of or, a previously proved theorem. P or true equivals true. All right, the next thing we're going to prove is 3.42. P and not P equivals false. So here's the proof. We're going to start with the side that has the most structure, P and not P, and we're going to get it to equival false. So we're going to wind up at the end. What we need to do is we need to wind up at the end with false. Because P and not P is not a theorem. The theorem is P and not P equivals false. So we will start with the left-hand side and get it to the right-hand side. Okay, well, obviously we're going to use the golden rule. 3.35. And everywhere there is a Q, we will replace it with not P. And everywhere there is a Q, we will replace it with not P. So what do you have? Can you visualize it there? P and not P equals not P equals P or not P. So what is P and not P? It's P equals not P equals P or not P. Okay, are you with me? All right, now what's the next step? 3.2, symmetry of equivalence. Which equivalence is going to be, which equivalence are we going to use to flip around? I think it's the first one. We're going to replace the P equals not P with not P equals P. So do you see how we switch those first two ones around? And then we bring down the P or not P. So that's symmetry of equivalence. And then the next step is 3.15. Now what is 3.15? Let's take a look. It's not P equals false. We actually proved this. I don't know if you remember that, but we proved this in a previous lecture. So we have not P equals P, and so what does that equal? It equals false. So let's go back. So here we are at 3.15, and we said that not P equals P is the same thing as false. So we have false equals, and we bring down the P or not P. Now we are going to use excluded middle. Okay, now here's the thing about excluded middle. Let's take a look at excluded middle. 3.28. Here is excluded middle, 3.28, and it just says P or not P. Now, the way you use excluded middle is anytime you have P or not P, you can replace it with true, because all theorems and axioms are equivalent to true, because true is one of the previously proved theorems. So the way you use excluded middle in a proof is anytime you have anything of the form, any Boolean expression of the form P or not P, you can simply replace that with true. So let's do that. So here we are, 3.28 excluded middle, and we are going to replace that P or not P with true. So what will we have? False equals true. But what are we trying to get this to? We were trying to get this to false, right? Well, that by 3.3 with Q replaced by false is false. And we have gotten the left-hand side equivalent to the right-hand side. And that concludes our Lecture 10 recap. See you next time.